Hello, am I audible? Hello, hello, hello.
Yes, hello, Muhammad.
Hi, am I audible?
Yes, I can hear you very well.
Okay, okay. Let's wait for 5 minutes before everyone will join or who is
Okay.
interested. Okay.
Yes, yes. Lecture or the problem sessions are uploaded. Thank you, Muhammad.
Yeah, sure. Actually, they did that themselves before I could ask
Mhm.
them.
Okay.
So, was this week on MOS transistors, right? So, have you guys studied anything related to MOSFETs before?
Yes,
Okay.
I am graduated from Electronics and Communication Engineering,
Oh,
but I am
okay.
not in India, by the way. I'm in Egypt,
Okay, okay.
and I'm currently pursuing my Master of Science.
Okay, nice.
Are you working, Muhammad, with
Actually,
Professor Imam
I
Handal?
no, no, no. Actually, I work on devices and
Mm-hmm, mm-hmm,
the TA work. This is a Prime Minister's Research Fellowship. This is one of the schemes for PhD students here in India. So
mm-hmm,
this
mm-hmm,
fellowship was awarded to me last year,
mm-hmm,
and
mm-hmm.
as a part of that duty, we have to do this NPTEL sessions that rounds up to 50 hours in a year.
Mm-hmm. How much hours per week?
Per week, 2 hours.
2 hours.
Yeah, you have to give this session. That's all.
Mm-hmm, mm-hmm, mm-hmm. You are in which year in the PhD?
Okay, I just completed my third year. I'm a direct PhD student. I have not done masters.
Mm,
So from my graduation, after my graduation, I directly joined PhD here at IIT Kanpur.
mm-hmm. IIT Kanpur. Okay. Nice to know you.
Uh, Same here.
Thank you.
Are other guys, all the undergraduate students who have joined?
Good evening, sir.
Good evening. So are you guys undergraduate students? You have muted yourself, Sanjeet. Hi.
By the way, Muhammad, I have returned to the. Do you remember the last question that we have talked that involved the two diets?
Yeah, yeah, yeah. Electrical diodes.
Yes,
So
yes,
I
yes.
wanted to say
I,
one thing about that as well. Okay, we can just discuss after 6-5. Let's wait for 2 minutes. People are joining still. Or I
do
guess
you
we
want?
can. I guess we can. I think start. Yeah. Do you have anything to say?
Yes, yes. I have understand that when you draw the characteristics and said that at a
Okay.
certain ranges of current, we can assume that
Mhm.
the same voltage that is dropped on D1 will be the same dropped on D2.
Mhm.
Yes, and I told you this is an approximation.
Okay.
Yes, this is involve a little bit approximation, but it's acceptable. But by
Mhm.
the way, using the exponential model of diode, we can have two diodes that are having the same voltage, but moving
Different.
different current.
Yeah, yeah. So let me just discuss about these two things: a voltage source and a current source, right? So when you have a voltage source here, and you have anything, let's say any component here added, you don't know what it is. Let's say this is ground, this is ground. No matter what current what current flows through here, this voltage, this potential difference remains same, right?
Yes.
Is it true? Similarly, let me just draw for the current source as well. Now, if you have current source, no matter what potential you keep here, let's say I have some dummy potential here. No matter what potential you increase here, this current will remain constant, right?
Yes.
Okay, wait a second. So now let me just draw the characteristics. When we can treat, let's note, when we can treat device as a current source and voltage source. So if you somehow come across a device characteristic such that it's for example VD is a drain voltage, you have this type of characteristics. You have seen this in MOSFETs, right?
Yes. Yes.
So this is I said. So if you come across a current device which is working in this region, right? You can simply model it as current source because no matter what voltage you increase, like here, your current remains constant. Similarly, if you have device characteristics that work in this way, let's say in this way,
This is a voltage source. Yes.
yeah, this is a voltage source.
Mm-hmm. Mm-hmm. Mm-hmm.
Okay, so this is how you approximate the characteristics of the devices. Let's say.
Mm-hmm.
Okay, so,
Mm.
so
But
today's
but by
topic.
the
Yeah,
by the way, I want to tell you something.
yeah, please.
Uh, this is this is is okay when in the question he said assume the voltage drop model, assume the voltage, assume the diode is a battery source or a voltage source. We can do this, but when he is telling us use the exponential model, we are not able to make this. By the way, and I want to tell
Mm-hmm.
you something else. The last thing.
Mm-hmm.
By the way, when you said that if these two died, a second please, second. When you said that if these two diodes
Mm-hmm.
are made from the same material,
Yes.
okay, so they are going to face the same, they are going to change similarly and will
Mm.
drop the same voltage on them,
Yeah. Yeah.
okay. But I want to tell you remember these words, right?
Mm-hmm.
But I want to tell you something. In order to have two diodes
Mm-hmm.
using the exponential model, in order to have these two diodes that will have the same drop voltage, they must be from different materials, because the only different that will make two diodes have the same voltage and move different current is having different reverse saturation current.
But you
A
are
different.
operating the device in, what
You
can I
got my
say?
point,
For
Mohammed?
no, not completely, but you need to do the devices in forward bias, right?
Yes.
Okay.
Hmm.
So,
And
Mm-hmm.
Yes, the
Yeah, yeah, please complete.
exponential model involves IS exponential VD over V thermal,
Mm-hmm.
assuming that we are going to neglect the minus one factor. So if we assume this, in order to have the same potential and different current, we need to
Mm-hmm.
have different reverse saturation parameter. And to have different reverse saturation IS in the different we need to have different material MOSFETs made, sorry, diodes made of different materials.
So, but that will change the cut-in voltage as well.
Yes, that
The
will change
pot
the cut.
the potential drop when you model the diode, we applied minus V diode by some resistance. Let's say when you apply this model, you keep this potential as a this is a cut-in potential, right? So
Mm-hmm,
this remains fixed for every diode. It will only remain fixed for every diode when they are of the same material.
mm-hmm,
So you cannot use one diode of silicon and another diode of germanium that may have same V gamma. V gamma here represents cut-in voltage.
mm-hmm, mm-hmm,
As I said, this is a voltage source. When device is operating at higher bias than the cut-in voltage, it simply works as a voltage source.
mm-hmm,
Like for example, the device is here. Just look here. If the device is operating in this region, I have just shaded this region. No matter what voltage you increase, you get a constant current, right?
yes, yes, yes.
Okay, so you have here, let's say, resistor, you have a transistor. No matter what voltage you increase from drain to source, the current remains constant. Okay, this is the definition of current source. Similarly, in this type of characteristics, no matter what voltage you increase, your current and voltage characteristics will be in this manner, and it will act as a voltage source. So you have to just directly model it as a voltage. And for the diodes, as I said, there is a particular limit of the application that will be given in the specification sheet if you go on the website and buy the diode from some company. So it has a limit. You cannot just go on increasing. As I said, if you are graduated, you may know the band diagram from the band diagram point of view as well. You cannot go on increasing this VBI minus V, right? This is a particular limit. This restricts your cut-in voltage. Okay, you just cannot have a conduction band that is somewhat like flat. It will just burn the device.
Mm-hmm, mm-hmm,
So it will just act as a voltage source.
mm.
Okay,
Okay, okay.
okay. So so let's have a little bit of basics about MOSFET first. Okay, so let me just draw a basic schematic of a MOSFET. Okay, this is a very basic schematic. G represents gate, D represents drain, S represents source. Now I have made here N plus, here N plus represents highly N2, right?
Total.
So what is this? This is a P valve. So can anyone tell me how does the MOSFET or MOSFET operate? And what are the three regions of the MOSFET operation?
Ohmic saturation and
Mm-hmm.
cutoff.
No, no. What are the three regions? If I go on increasing this Vg from some minus Vx to plus Vx, so how will the device behave? What is this region? This is accumulation, right? I will just explain a bit about it as well. And it will just reach here as a depletion or weak inversion, and at higher biases of gate voltage it will go to strong inversion. So what it is actually? So you have this MOSFET, and you have this gate. So initially this is a filled with holes, right? So when you apply negative voltage here, what happens is these holes start accumulating in this region, right? So the term accumulate, right? The holes will start accumulating at the interface. This is a dioxide. Okay. So this is called as accumulation. Similarly, if it is a N1, then on the application of positive voltage, electrons will accumulate in this region. So that will be the accumulation for P channel device. Now another is depletion in weak inversion. I will represent weak inversion by Wi. So that means then when Vg is positive, okay. So when I apply a positive voltage, what will happen? Can anyone tell me what will happen?
Yes, yes. This holes is going to be repelled,
Okay.
uh, and
So
some ions will be surfaced out. Is going to appear in the channel.
okay. So what happens is this is a P well, right? So can I say that in P well I have two carriers, holes as well of electrons, right? Holes are greater than electrons. It's true. We just had studied this in first session. So what happens is when you apply the positive gate voltage, these electrons from P well and from these contacts as well from drain and source. This is drain, this is source, because it contains N plus. N plus has a high amount of electrons. 1 second. So it has a high amount of electrons. So on the application of positive voltage, these electrons start to accumulate at the interface. But what happens is, since it's a P well, it has Na. Na is acceptor atoms, right? So what happens is Na gains electrons and it acquires a charge of negative, so it becomes Na negative. So what happens actually is at this depletion, let me just represent it with gate, we have negative ions here. So this is called as, sorry, this is called as depletion. So what happens at larger gate biases? At larger gate biases, more electrons at the interface become nearly equivalent to hole concentration in the bulk. Bulk means this is called as a bulk. Okay. So this is called as inversion. and device operates in inversion, that also we call it as an on state. Okay. So we have three regions. If I draw a device characteristics, let's say in this way, let's say IDVG, you will see that it has a almost similar characteristics as that of a diode. So let me just see here. This will be depletion and weak inversion. Then for example, for this region, after a particular threshold voltage, here it is will be strong inversion. But in you must have gone through the assignments, right? In assignments, you guys would have used only this expression, right? So can you tell me how this expression comes? Anyone?
Yes, when VDS is equal to VGS minus V threshold pinch of voltage, if we substitute in the current voltage equation, we are going to come up with this formula.
So this relation comes when your drain bias is equivalent to your VGS minus VTH, right?
Yes, yes,
So VGS minus VTH is called as overdrive voltage, right?
yes, yes.
So all the other students, do you know about this relationship? Anyone from let's say BTech first or second year? 1 second. Okay. So for the MOSFET, you know that your IDS is UNCox. It's for the N-channel MOSFET. W by L VGS minus VTH multiplied by VDS minus VDS square by 2, right? This is a MOSFET equation. Like you have for diode, this is how we model the MOSFET. Okay, so if you just see this IDVD, you will notice that it has this region. This region is called as anyone, and what is this region called as?
Starting region is ohmic and second region is saturation.
Okay, okay. So we have linear region as well as saturation region, right? But in all of your questions, you will see that your device is mostly in saturation. So how do we define that? Usually, this voltage here, it comes out to be nearly equivalent to VGS minus VTH. This is called as actually pinch off voltage. Okay. So after this voltage, if VDS is greater than or equal to VGS minus VTH, the device goes into saturation. Okay. So let me just substitute it here. VDS is equivalent to VGS. This is a minimum condition. My IDS will be, if you substitute it in this equation, IDS equation, you will see that this is mu and Cox divided by L. This comes out to be VGS minus VTH whole square. This is your saturation current. Okay. Any questions till now? Because now we will start doing the assignment.
Yes, I have a question, sir.
Yeah, yeah.
Always when we find questions or when we see questions about MOSFET, we always ask it to determine whether the device in the saturation, in the linear,
Hmm.
in the cutoff.
Hmm,
But
hmm, hmm.
how to determine that the device is in weak inversion, strong inversion, and subthreshold
That
or
okay.
depletion?
Okay, so that you cannot directly from the IDBD characteristics. Wait a second. Second. Okay, so you can determine the regions. You can determine from the IV as well. If you have IDVG characteristics, you will see that in subthreshold, you have in log scale current, you have this kind of operation in log scale, log of ID. So this is your subthreshold characteristics. But if you want to accurately determine the characteristics and derive the parameters, some, for example, C aux, C depletion, so you need to know the capacitance characteristics of the device, determine the region of operation. One second. So you must have seen on the capacitance characteristics, this is VG, right? This is
Mm.
C by C. This is will be your accumulation region. This is your depletion capacitance, and this will be your strong inversion. Okay.
Okay, if I have a certain potential that has been set or established or applied on this device, how from this potential I can determine whether it is biased in the strong inversion, weak inversion, or moderate inversion?
Okay, for that condition, you have to check if you want to first, you have to, if you are given some potentials, right?
Mm,
You must have seen in the questions as well. If you are given some potentials, you calculate the, let's say VGS, you are given VTH, right? You are given other
mm,
parameters, you just calculate VDS if it is greater than or less than VGS minus VTH. If this comes out to be minimum is equivalent to VGS minus VTH, that means your device is in saturation.
yes.
Mhm.
What about moderate inversion and strong inversion?
No, no, you cannot find that from your IV characteristics because and yes, if your VGS, if your VGS is let's say less than VTH, okay, and
Mm-hmm.
it is conducting current.
Mm,
So it is conducting a positive current. That means it is in moderate inversion or weak inversion, right? So
mm,
if you go on checking it, when your VGS is VTH plus some 6 times phi t. Phi t is it's I guess it's 4 times phi t or 6 times phi t. I don't remember exactly. But if it is VGS is equal to VTH plus 6 times phi t, let's say I will just keep this 6 as a number here right now. That means your device is in strong inversion. And if your VGS is less than VTH but it is conducting, that means your device is in weak inversion or in a moderate inversion. Near about, you can say that in near about VTH, and you know if your VGS is negative, that means your device is in accumulation. You can check this by mostly using if you have a capacitance characteristics. If you can plot the capacitance characteristics, you
Mm,
will be more, it will be more easy for you to understand how, where is your device operating.
mhm. And what will be different if the device is in weak inversion or strong inversion
Okay,
or
yes.
moderate?
Okay, so you know your current is basically what? It's charge into velocity. Hmm?
Mm?
Your current is basically charge and how much fast they are moving, right?
Yes, yes.
Okay, that means it depends on charge. This current depends on charge, and it depends on velocity, right?
Mhm, mhm,
Let me just assume velocity is constant,
mhm.
and if you have
Velocity is
charge,
controlled by VDS and the charge is controlled by VGS.
yeah, charge is controlled by VGS. Now, if it is in strong inversion, that means you will have a large amount of current, right?
Mhm,
If you have in moderate or weak inversion, you have less amount of current. So that will you will see in IDVD characteristics. Okay, this is how it is here. Let me say this is near threshold voltage. You will see a very less amount of current here. You go on increasing the VGS towards the strong inversion, you have a large amount of current. Okay, that will be the difference. The current amount of current that flows through a device will be different.
mhm, mhm,
Okay.
mhm. And we are changing VGS and changing the current values according to the specs required to achieve, right?
Yes.
So it is not regularly should be in strong inversion or not regularly to be moderate. It depends on the specs needed, right?
Yes. 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 Usually, what happens is if you are, for example, let me just draw one more page here. So, if you are going to design an amplifier, let's say, you know that if this is your the company from which you buy the device or you have the device, you have characteristics, let's say like this. Okay, so for a particular application, you may have particular VGS. Let's say this is one VGS is equal to zero point 0.1, VGS is equal to zero point 0.2, VGS is equal to zero point 0.3. Let's say this is VGS is equal to 5 volt. Let's say kind of okay. Go on increasing the VGS. You have go on increasing the current. For a particular application, you can keep your device in any of this range. Okay,
Mhm, mhm,
this is called as an operating point.
mhm.
Right.
Yes,
Okay,
yes.
let's move on. Okay, do you have tried this question? Everyone else, can you please tell me?
Yes, sir.
Okay, so this is a PMOS, right? How do you know? Obviously, it's given as a minus, but you can see from the notation as well as here. Just to remember the notations, you can just keep this in mind that it is like this. PMOS means this is a P channel, right? P plus, P plus, and this is N. And you know the symbol for diode is like this. So your current is, sorry, your symbol is here shown. One second, let me erase it. Here is shown like this. That means this is P on this side and this is N on this side. So this is how you can remember it is a PMOS or an NMOS. In NMOS, you will see this will be given like this, right? Because it has a P well here and this is an N contact, N plus contact here. Just remember how you can remember whether it is a PMOS or it's a NMOS. So you don't have to do any on the analysis, because you just have to change the polarity of your applied voltage, you will get the same answers for both. If I, for example, use an NMOS here as well in the question and just change the sign, you will get the same answer. So let us see. We have the device given. Vt is given to us as zero point 0.9 volt and K is 28 millisiemens. K here is nuance ox W by L. Okay, this is what I have written here. Just, okay, if Vx is now 1.9 volts and Vx is small Vx and capital Vx, just know the difference. Vx is 1.9 volts, that's a DC, and Vx small 4 millivolts, that is AC. What is a small signal current ID? We have to find small signal current ID. Give an answer in the convention, the current. Okay, so you now know. Do you know small signal equivalent circuits? Okay, we can just directly write in this question as, you know, your small ID is simply GM times VG, sorry, VSG, right? But to calculate GM, we should know what is ID, right? So my ID will be simply equivalent to V of VSG minus VT whole square. And this is given to us. That is 28 milli, and VSG. This is your G, this is your source, and this is your drain, right? So my VSG will be VS minus
1.4.
hmm?
1.4, I think.
Okay, let me just check. 28 milli. VS is at 3.3 volt, right? And VG is at VX. VX is 1.9 volt, right? It is connected to VX. Can you guys see? Minus 0.9 volt square. So is this correct? Can you see? Okay. So my ID will be, but okay, sorry, we don't have to calculate ID. We have to calculate GM, right? So that will be more easier to calculate. GM is simply DID by, we can
By
just directly,
division.
yes, DVG. So that will be simply 2K VSG minus VT, right? So you can see it is 28 milli. That will be here, this number. So what is the value? What is the value for GM? Let's just calculate it. This is 3.1.
28.
Okay, into 2 into 20. It's 28, right?
Mm-hmm.
Then we have to find ID. That will be simply equivalent to GM VSG. Okay, that means GM is 28 multiplied by VSG. But here know that this VSG is small signal, right?
Mm-hmm.
So now you may have seen in small signal what VD will be ground, right?
Mm-hmm.
And this will be connected to Vx. So this is at 4 millivolts. So and this is Vs at 0. So it will be simply 4 millivolt. Forget about the sign, because you just need to know from what direction to what direction the current flows. Okay, current always flows from drain to source, right? So but in NMOS, your drain is at higher potential, your source is at lower potential. From top to bottom, current flows from top to bottom in NMOS. In
Excuse
PMOS,
me, sir.
hello,
सर वैल्यू ऑफ जैसे 1 minute.
Okay.
वैल्यू ऑफ के असाइनमेंट में जैसे 38 दिया हुआ है।
Yes.
हाँ, एंड वैल्यू ऑफ बीटीएस की 1 दी हुई है।
Ouch. कि माइक से थोड़ा शोर आ रहा है, सुनाई नहीं दे रहा। एक्चुअली ये वाला असाइनमेंट इट शुड बी पहले हफ्ते तो मैंने दिखा दिया था, but it has to be different than the one you have to do. So questions will be more or similar than you have done in you have been given. And
ओके सर, ओके।
this discussion will give you a brief idea how to do the questions. That will be of the
ओके
same kind. Okay. So this is how you find the ID. Okay. Similarly, next we have this. I guess it's the same question. What is the difference in this question?
You have RD here.
Hmm. So my Vx here. Let's say this is V. Sorry, not Vx here. Okay. Let me just note it. This is my Vs. This is my Vg. Okay. Now we need to. Oh, 1 second. So what will be your approach to do this question? You must have tried this. Anyone? Simple. First we start. Okay.
I think it's going to be a quadratic equation in ID,
Hmm.
and then we are
Mhm.
going to solve it.
Yes, 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 yes. So I will just give you an idea how to solve this question. I will not solve this completely because that will be a basic quadratic equation formulation. So we have to find an ID here. Let me just denote it as ID. We assume the device is in saturation. So my ID will be K times, sorry, VSG minus VT whole square, right? It's good. But what is the VSG here? What is VSG here?
3.3 minus ID into RD।
Right. VSG is 3.3 minus VG. First we will write VG, right? But here VG is equivalent to Vx because it is shorted here, right? It is short. And your Vx is IDRD, right? So my ID will be K times 3.3 minus IDRD minus VT whole square. So now what you have to find is you have to find ID. Okay. So your K is known, 3.3 is a constant, VT is known, RD is given to us as 3.76 kilo. Now you need to find this is a quadratic equation. You need to solve the quadratic equation and you will find the answer, right? Anyone has any question in this part?
Yeah, but quadratic equation have two answer, right?
Yes, yes, yes. Yeah, right, right. Thanks for pointing that out. We have two answers, right? Okay. So now you need to check at last. Either you check the current or you can check directly the VGS minus VTH. Okay. Since your device has to be in saturation, so your VDS should be at least minimum should be equivalent to VGS minus VTH. So how will you calculate it? Your VDS is simply from this potential to this potential, and your VD will be governed by ID/RD. Okay. So the solutions you have for ID, you substitute it for VD, then calculate VSD or VSG. It's only the same thing. You can just calculate VSD equal to VSG minus VT. Okay. So You will get your answers from this as well. Okay. Or what you can do is that you can say that your VSG, or one more thing is, no, you can just directly, you have to, no, you cannot do that. You have to find it from VSG minus VT. Okay. You will have two answers. You substitute the value of ID, then you will get, you will substitute the values in this relation. Okay, where VSD should be greater than VSG minus VT. Okay. Okay, now this is an N-channel MOSFET. N-channel MOSFET means you have N plus here, N plus here. This is P12. Okay, that means on positive biases, device will be on, right? So what is the first step? You have to find here what is the maximum value of RD for which the device is in saturation. So I have to find what is the maximum. We know for the condition to be in saturation, VDS has to be greater than or equal to VGS minus VTH. Okay, here VD, this is my VD, this is my S, and what is VD here? VD here is, if we apply a KVL from top to bottom, okay, this is ground here. My VD will be simply equivalent to, if we just first calculate VD, it will be VDD, just VDD minus, if current of ID is flowing, so that will be IDRD, right? And my S is grounded, so VDS will be simply VDD minus IDRD. So my VDS will be VDD minus IDRD should be greater than or equal to VGS minus VTH. So for ID to be maximum, that means this RD has to be maximum and device has to be saturation. That means this term should be minimum at that time. And for minimum, we know that it should be then equivalent to VGS minus VTH. Okay? Right? You know now, VDD is known as 5 volts. We have to calculate ID. Your VGS, we will just calculate the VGS, and VTH is given to us as 0.4. Okay, they represent VTH as simply VT. Don't confuse yourself with VTH. Okay, so how will you calculate VGS? Can anyone tell me? This is G, this is S. So how will you calculate VGS?
Did we get VG or not?
This is VG, this is S. S is grounded.
Yes, VG
So,
minus VS.
okay, so how will you calculate VG?
VG, it is voltage divider,
Okay,
resistor divider.
Voltage divider.
okay, voltage divider between R2 and R1, right?
Yeah.
Okay,
Yes, yes.
nice. So my VG will be, just tell me if I am correct, it is R2 to 5 volts. Is it correct? R2 is 100 K divided by 100 K plus 575.7 K into 5 volt. Can you please find the answer? What is VG? K will go. There is a, comes out to be 0.74 volt. Okay, so my VGS will be VG minus VS, that 3.74 minus 0 because VS is grounded. So VGS will be 0.7. Okay, is it correct? So my R, to calculate now RD max. So what do we have here? This is VDD minus ID RD max. equivalent to VGS minus VT.
TH.
That means it is 0.74 minus what is VT? 0.5. Okay,
Point
and
five.
VDD is 3 volt. So it will be 3, sorry, it's not 3, it's 5 volt, right? 5 minus point, this is 0.24 is equivalent to RD max. So my RD max is, this is 4.76 divided by ID. So what is left is to calculate ID. Can you calculate ID? ID is simply K times VGS minus VT whole square, and this comes out to be K is given to us as 1.16 millisiemens per volt. VGS minus VT is just calculated as equivalent to 0.24. Can you please calculate it? This is nearly, this comes out to be 0.0668 milli. Okay. Now you just have to substitute it here. You will get RD max, right? Okay. Shall we move on?
Yes.
Okay.
Yes, sir.
Okay. So now the question says, in the earlier circuit, assume RD is 35 kilo ohm. 35 kilo ohm. Please first let's just calculate it. What is RD max? It is 4.76 divided by 0.0668 milli. Milli will go millimeter, that will be kilo. Okay, like it is equivalent to 71.4 kilo. Okay. Okay, this is now in this question it is given as RD is 35.5 kilo ohm. What is the maximum ID that can flow through the device such that the device is in saturation? Okay, for this question, ignore the values of R1 and R2. We know nothing about R1 and R2. We just know that device is in saturation. Okay, so what will be the first step? VDS min, right? Should be VGS minus VT, right? Okay, VDS min means VDD, as I said earlier, this is a simple KVL, RT, this is RD, IDRD is equal to VGS minus VT, right? Hmm, there should be some more information in this question. Hmm, okay. Okay, so my ID is basically VGS minus VT whole square, right? Now for the saturation, you know that VDS is VGS minus VT, right? Can I substitute it here? VDS square, right? Okay, and now you know that VDS is simply equivalent to VDD minus IDRD, right? From this figure, you can easily see my VDS is VDD minus ID current flowing through the resistor RD, right? So it will be ID is equivalent to VDS square, that is VDD minus ID RD whole square. Is it correct? Hmm. My VDD is 5 volt. I can just write it as 5 square plus ID RD square minus 10 ID RD. Again, this is a quadratic in
Yes, sir.
ID. This is a quadratic in ID. So you will again get two answers. Okay. So you have to again check from the VDS whether your device remains in saturation or not. You can just directly use this relation, then you can check. Mm, okay, no, you cannot. You don't know what is VGS, but you can check this relation from this relation, or so any other options from which we can check whether the device is in saturation, whether the answer is correct or wrong. Okay, you will find the answer. You just calculate it. Maybe there will be some option with negative currents. Okay, because we don't know about what is VGS minus VTH, so you cannot use this relation. You have to just solve this question. Solve it at your end. If you get two options, then we can check whether how to which one is the correct answer. That's it. Okay, for quadratic options, you will always get two options, right? Okay. Okay, so how this question? Was there any question of this sort in your assignments? Okay, now we have given that you have previous R1 and R2 values, which we used for which we calculated VGS as 0.74 volt. No, we have here RDS as well. Okay, this is RDS in drain side, so I can for yes. So my VGS is 0.74 volt and my VT is 0.5 volt. So my VGS minus VT is 0.24. Okay. Right? So due to the temperature and other device imperfections, the value of K is no longer as stated in Q3. What was the K in that question? Question number 3. K was 1.16. K was 1.16, but here it is multiplied by 2. Will the device be in saturation? So will the device be in saturation? So for saturation, VDS is VGS, at least it should be VGS minus VT. Let's assume the device is in saturation. We will do ID as K times VGS minus VT whole square. Okay. But at this time, you will use K as 2 into 1.16 milli. And VGS minus VT is 0.74, sorry, 0.474 minus 0.5, that's 0.24 whole square. Okay. You will get an ID of, this is the value of ID, to multiply by 1.16 multiplied by
0.13363
0.1.
336.
Okay, okay.
336.
This is milliampere, right? This is milliampere. Now,
Yes, sir.
what is VDS? This is VDD minus IDRD, correct? So my VDD is 3, sorry, Okay, why I'm confusing myself with 3 volt. VDD is 5 volt, right? What is VDD? VDD is 5 volt. So this will be 5 volt minus 0.1336 milli into RD. RD is given in this question as, okay, RD from question 4. RD from question 4 is 35.5 kilo ohm. So why are we calculating VDS? To check its relation with VG. What is its value? Is its value less than VGS minus VT or above or equivalent, right? So let us just quickly calculate what is 0.1336 milli multiplied by 35.5. That is 5 minus 2.25. Sorry, 1 second. 0.1336 multiplied by 35.5. Is
सर हमारी वैल्यू आ रही है 0.2572
0.
2572
257.
Okay, so now see here, my VDS is 0.2572, right? So can you now see from this relation VDS minimum should be VGS minus VT. Can you see that here VDS is greater than VGS minus VTH?
yes
Yes.
sir greater
Yes,
than
sir.
So your device will
Yes.
be in saturation, right? Or
Saturation.
okay, so
Situation.
assumption was correct. So this is how you do
सर
this question. Yes.
इस ऑप्शन में एज ऑफ सेचुरेशन दिया इसका मीनिंग क्या है
What? Okay, so edge of saturation means you can say that when VDS is accurately or exactly equivalent to VGS minus VT. Or you can say that since it's very close, 0.2572, it's not, okay, so there are two options. I didn't see this option as well. So it is at the edge of saturation means your VDS is very, very close to VGS minus VT. So in this question, the answer is it's not well in saturation because it's at the edge. It's only a 0.01 volt difference. So answer will be edge of saturation, not well in saturation. Thanks for correcting, Sanjit.
ओके सर
So if it would have been greater than VGS minus VT, so we can then say that it is well in saturation. But as we can see, it's the only difference of 0.01 volt. We can say that the more accurate answer will be, it will be at the edge of the saturation, right? Okay, now one more question. So again, this is called as a one more thing. A term here is called as source degeneration. Just remember that. So adding a series, adding a source resistance in a MOSFET is called as source degeneration. It lowers your gain actually. Okay, so we'll see in the last question we have to calculate the gain as well. We'll see that. Okay, what we have to do is, okay, we have this relation ID. Solve the circuit and arrive at the operating point. Operating point, what do you mean by operating point? Operating point is simply what is your ID, what is your VG, okay, what is your VGS, okay, what is
Your large signal quantities, right?
not large signal quantities, it's DC. DC, what is your DC conditions? Okay, so my, for example, VD here, what is your VDS? These are some operating point variables, okay? On top of it, you apply some small signals, okay? So, but here in this question, we have to calculate an operating point ID, okay? Operating point means simply what is the device, current, voltage, and everything else, okay? So in this question, we have to calculate the ID and we have to give answer in microamperes. So can you just see that it again will be something related to quadratics? Hmm? Because we have the source degeneration again. So first what we will do is that we will calculate Vg, right? Vg will be again by source voltage divider. That will be R2 divided by R1 plus R2 multiplied by 5 volts. Okay, you have your values given to as for those four resistors. Can you just quickly calculate it? What is R2 divided by R1 plus R2? R2 is 327 divided by 654 plus
1.667 volt.
1 point,
667.
okay, 1.667 volt. Okay, nice. So what will be VGS here? Can you directly write VGS as 1.66 volt in this question?
No, no.
1.667 minus IT into RS.
Okay, yes, that is the catch here in this question. You have to check for ID multiply RS. Nice. So my VGS will be simply equivalent to Vg minus Vs, that is Vg minus ID RS. Okay. So what will be your ID? Simply K times VGS minus Vt whole square, right? Again, just let me just write it. So you just calculated Vg. Now you have a Vs as IDRS minus Vt whole square. This comes out again as a quadratic equation with Vg as 1.667 as you said, and this is minus. Okay, so this comes out to be 1.667 minus Vt. Vt is given to us as 0.5 volt. Okay, so this will be 1.167 minus IDRS square. Okay, this is again a quadratic equation. So you need to solve for questions after that. You need to answer this. So I have just kept the answer for this question for ID is this is 47 microamperes. Okay, so you solve the quadratic equation at your end. You find the two answers, then you check the saturation condition. Then you will reach to this answer of 47 microamperes. I have written this because it is needed in the further questions. Okay, so this was again a simple question which I have discussed earlier as well. Simple quadratic formulation. Okay, now we are told that compute the small signal GM, sorry, not gain, of the N-channel MOSFET. Give your answer in microsiemens. So that will be your simply ID is K times VGS minus VT whole square. As said in the first question or second question, we know that GM is simply dID by dVG. Is it right? Right.
Yes, yes.
Okay. So you know that it will be 2 times K. What is K? K is given to us as 4.7 millisiemens. Okay, and VGS, we need to calculate VGS. As I said, we need the value. That was Vg minus Vs. That is 1.667 minus IDRS. Okay, so that is 1.667 minus ID. What was ID? 47 microampere multiplied by RS. RS is given to us as 22.7 kilo ohm. Okay, so can you quickly calculate it?
Yes, sir. 0.6001.
0.6001. Okay, this is in volt. Okay, make it a habit. Just a suggestion that always, whenever you say the value, say units with it as well. So it is a good habit. It will help you future. So, and you will just remember the units as well. So say it's 0.6001 volt. Okay. So my GM now will be 2 into 4.7 milli. This is 0.6001 minus VT. VT is zero point 0.5, right? So what is the answer?
939.06 microsiemens.
Microsiemens, right? What is the Siemens? What is Siemens? Siemens is inverse of ohm, right?
1/ohm.
Okay. The GM is called as transconductance.
Transmitter.
Hmm. Okay, so we found it. It is at 939. This was asked in the question.
And what
That's
is
it.
K, Muhammad? What's K?
K, as I said in the first question, it is actually mu and C ox W by L, which is 2. And you
Yes,
know
what is the name of K? What is the name?
what is?
What we call K? Yeah, we call GM transconductance. What we call
Okay,
K?
you don't call K anything. This is actually a
It is a
small.
constant.
Hmm? Is it
It's a
called some?
constant.
Yeah, no. Yeah, it is a constant for a particular device because you know that what is mu n? Mu n is a mobility, right?
Hmm.
Mu n is mobility. C ox is
Oxide capacitance.
oxide capacitance, right? And W by L is aspect ratio.
Mm-hmm.
Expectation.
Hmm. So K is just a small notation to represent these terms. Okay. So it's better to, if you want to just remember this relation, it's better you write it in full form, mu and C ox W by L. Okay. So this is just a constant for these. It has a unit. Its unit is, so okay, it is somewhat milli. It's Siemens per volt square, I guess. Maybe it is given. It will be given here. Okay, it is Siemens per volt. Sorry, it's Siemens per volt, not volt square. Okay. Okay. Now we have this question. Okay. So here we have the capacitors as well. The capacitors are so large that they behave as a short circuits for time varying signals. What is time varying signals? Let's say we have sinusoidal signal. Okay, this is my amplitude. This is my type. Okay, so assume the MOS device characteristics are perfectly flat in saturation. That means here, this region. Okay, this is completely flat. That means there is no dependence on VD. Yes, okay. All the resistor values in device parameters are given in earlier. What is the small signal gain of the circuit? Has anyone tried this question?
Yes, sir.
Okay,
With the help of formula G minus GM into RD.
oh, so do you know how you get that? You have to find the gain. Do you know how you get that term? GMRD. You said that it's GMRD, right?
Yes, yes.
So
Yes.
how do you achieve this formulation for the gain? Do you know?
By substituting this circuit with the incremental equivalent model.
Yes. Anyone else knows what does Ahmed say?
Yeah, small signal model that voltage source is zero. Incremental, constant voltage source is zero.
Okay.
VDD.
So
Yeah.
so yes. So what you do is that all the DC biases you short them. Okay, short or you ground them at the terminals.
Yes.
Okay, capacitor. Here in this question, it's assumed that they are shorted, so they are shorted. Okay. Now see here, if this is short, so what will it do? Okay, is this correct? Did I did the right or wrong?
Yes.
Because
Yes.
for the small signal, RS will not affect anything because this is short from this node to this node. Similarly, here this will be short. Okay. So if I draw equivalent circuit,
R1 parallel to R2.
so I have V in here, I have short here, shorted the capacitor. As I said, second, this is R1 parallel to R2, right? This is
Yes.
my gate,
Yes, sir.
this is my source that is shorted, and this is GL, VGS. I'm ignoring the, since VDS is, there is assumed that this region is flat, so their RDS is 0, okay? Not 0, sorry, not 0, it's infinite, okay? So here, there is usually other term that is called as RDS, and this is RD, right? Since this is infinite, so it won't affect us because no current will draw through here. So every current will come here and go here, right? And since this is also shorted, so this node is simply as V out. Have I drawn the correct? Please have a look at this equivalent circuit. Can you please tell me, is this correct? Hmm?
Can you repeat the question again?
I'm just saying that, is this correct equivalent circuit?
Yes.
Okay, so my RDS is infinite. Everyone understood why RDS is infinite?
Why RDS is
Infinite. Here,
ah
you see,
because RDS is the slope of ID versus VDS.
okay, so you are operating in the saturation region, and RDS is DIDS by dVDS. That is equivalent to, sorry. This is RDS inverse. Okay,
RDS
reciprocal of it.
inverse.
Yeah, so my RDS will be 1 by 0. That will be infinite.
Infinite.
Okay, so RDS is infinite. So whatever current is flowing through this terminal comes from RD. So what is the current flowing through RD? Can you tell me? Just look at here. This is a node.
Zero.
No, no, not 0. This is a
Negative
node.
GM VGS.
This is a node here, current leaving, and there is some current coming. So the current will be GMVGS, right? So the current here will be
Yeah.
GMVGS. But you are calculating the potential from this node to this node. Your potential will be minus times GMVGS
VGS.
RD, right? So my VGS here, since this is V in here, so V in will be here as well. So my VGS is V in simply. Okay, so my V output is minus GM RD multiplied by V in. So what is the gain? That is output voltage
Minus GM RD.
by input voltage. Okay, so my gain will be simply V output by V input minus GM RD. Okay, right? So GM you have calculated in the previous question, right? That is 939 microsiemens. You can just calculate the gain in this question now because you know the RD, you know the GM. Any question? Any doubts in this question?
सर सर जैसे ऑप्शन में निगेटिव और पॉजिटिव दोनों दिया तो कौन सा चूज करनी होगी?
Because the gain it will be negative. You don't have to. Uh, if all are given as positive, then just check the magnitude. Otherwise, for this amplifier, there is a change of phase of 180 degrees due to minus sign. So you have to consider minus sign as well. So give the option with minus sign.
ओके सर.
Okay.
Yeah, yeah, means inverted waveform we get.
Yeah, inverted waveform. So you have to consider the minus sign as well.
Okay.
Okay. So this is the question number 8. Okay, what is the next question? To maintain the internal device in saturation, VDS, we know now this. In earlier circuit, what is the maximum value of RD for which the device remains in saturation? Now, can you do this question now? Simply the way we did it earlier, but here just a thing that you have to consider here, because there is RS as well. Okay, so you just need to be careful with it, because now if you just draw a KVL from this node to this node, what you will see, your VDD will be equivalent to IDRD, drop across the resistor, plus drop across VDS, right? Plus also, due to series resistor RS, there will be IDRS drop as well, right? A simple KVL from this node to this node. Okay. Again, basic. We have to say that it's a maximum RD. That means condition is VDS should be equivalent to VGS minus VT. Substituted in here, that will be VDT is equal to IDRD plus VGS minus VT plus IDRS. Okay, so my RD maximum, we have to calculate the maximum RD. Since at this condition for VDS is equal to VGS minus VT, RD reaches maximum value. Some people are joining now. Okay, so this is again a simple formulation now, because we know ID now. Okay, we know RD as well from the ID as ID is 47 microamperes calculated in question number 6, I guess. We just have, there is unknown variable only is this RD max, because RS is also known. So okay, you can calculate it now. It will be simply equal to VDD minus VGS minus VT, sorry, minus, okay, this will be IDRS divided by ID. Okay, so substitute the values and you will get the answer. Okay, so we have the final question. This is again same as we did for the one when there was an increase in K. It's the same answer, same question. So you again calculate the ID simply given by GS minus VT whole square. You know that now again VG is equal to VGS is equal to VG minus VS is equal to VG minus IDRS. Again, it will be a quadratic equation. You have to solve this. Or solve one or two questions, you will get a good hand on it. That will be easy. Okay, so you solve this, you will get two solutions. Then substitute it back in the condition for the minimum saturation, and you will get the perfect answer. Okay, so this was all the question set that was on the MOSFETs for this week. Okay, so if you have any doubts related to this session, you can please ask me.
सर असाइनमेंट नंबर 1 में डाउट है.
Okay.
क्वेश्चन नंबर 1 का आंसर नहीं आ रहा था. जैसे असाइनमेंट नंबर 1 का आंसर नहीं आ रहा था, उसमें ऑप्शन ही नहीं मैच कर रही थी.
Okay. Are you talking about the question? Wait, I don't check. Let me check if it is here.
कुछ इटरेशन करके
Assignment.
This question?
यस सर.
Okay, this question I think has some. That is the solution. Wait a second. Okay, this question has, I guess, where the data is not, I guess, given correctly. Option, I think, मेरा भी match नहीं हुआ था. Okay, we have left it here. Okay, I think this question has some mistake. as far as I remember, because I was reading last week, I tried to solve it. I guess I also was not able to get the right answer for this. Anyone else can help him? Anyone else want the right answer for this question? You can discuss among each other. We have still time left for it. Anyone? Ahmed, have you tried this first question?
Actually, the in the that question VD is 961.01. We get. I have get
In this, which question you're talking about?
first question. Diode. There
Okay.
is a VD. Yeah, VD. That natural log.
Mhm.
And after that 258.
So, did you get any answer in the options?
No, 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 not match. I just click nearest answer.
Hmm. So that's what I said. There is a some mistake. Ahmed, did you get the answer, or anyone else get the answer?
I didn't try to get the final answer of this question.
Okay. I think I had tried this. Maybe let me just have a look. Mhm. I will just tell you my answer. Okay. I have got ID as 2 milliampere. What is the ID you got?
सर मेरा आईडी की वैल्यू आई अबाउट 2 मिली एम्पियर के आसपास आई थी।
Okay. Mine is also 2 milliampere. So there is something, some mistake in the question. Just don't need to worry about that. The important thing is that you should learn. That is the more concern you should have. You just learn how to do it and what is the basic operation of diode. And you should be confident enough to tell you the tell me or tell the assignment who make the assignments. You can just drop that in your form. You have the form from the NPTEL. You can just mention that the question one, the detail is not correct. If anyone else has found the answer, he can mention. Otherwise, you can just ask on the phone because we are not those. There are other maybe 2 or 3 peers will be also there. They can tell you that whether the question has a
हेलो
mistake or
सर।
not. Yes, yes.
सर इसी असाइनमेंट लास्ट वाले क्वेश्चन जो आप बोले थे बाद में डिस्कस करेंगे अच्छे से, फोटो
Okay.
डायोड वाले।
Okay. This question.
यस सर।
Okay. So, have you studied about photodiode?
यस सर। और जो आगे जो सॉल्व किए थे क्वेश्चन वो अभी क्लियर नहीं हुआ था, कैसे कैसे मतलब आया था जो टर्म।
कौन सा वाला?
ये वाली वी एल बाई वी टी, वी ओ बाई
Uh, this one.
और आ गया।
ये.
नेक्स्ट। हाँ हाँ यही।
Okay. क्या इसमें क्या दिक्कत आई थी आपको?
जैसे मैंने सॉल्व किया उसको डिफरेंशिएट किया था तो वी एल बाई वी टी कुछ करके बन ही नहीं रहा था सर, और ये वी ओ बाई वी टी।
Okay. VO by VT or VL by VT. It's
यस सर यस।
okay. So what was the power relation you wrote? Simply PL multiply by 1 second. Okay. So this is your power relation, right? PL is equal to VL into IL. Okay. Now you have this I naught. I naught will be ID plus IL, right? That's for it's correct. Okay. So
यस सर।
then you have IL as I naught minus ID, and you know that for diode IS. Anyone is saying anything? Okay. So IL will be of this form. Substitute it in PL now. This is your IL. Let me just denote it by star. You have to substitute it in this expression. So you will get, just see, it's not erasing it. So my PL will be simply This is VL here. This is VL here. Okay. This is I naught minus Is exponential of VL minus 1. Okay. Is it fine till now?
Yes, sir.
Okay.
Yes.
So now to find the maximum value, you have to differentiate it to something, right? So here variable is VL. So you differentiate it to VL and substitute it to 0. I told you that you will get a value of this form. Okay. Let me just write one or two steps so maybe you will get an idea. Okay. So I told you have to write it as 0, right? So till now you got this relation, okay, right? So just differentiate it with DL. You can see that this is a form of UV rule. You know differentiation UV rule? Differentiate one and keep the constant other term, differentiate second term, keep the constant first term. Know here that this is VL, first term will remain constant, then differentiate the second term, this the term in the bracket, and keep VL as it is. So you will get a term like this. And substitute it is 0, you will get here a term like this, I naught plus Is minus Is exponential of VL by Vt minus Is VL by Vt exponential of VL by Vt equivalent to 0. Did you get anything similar like this?
Yes.
Okay, so you will get I naught plus Is, okay, is equivalent to transport it to the RHS. You will get Is, taking some terms as common, Vt exponential of VL by Vt. Okay, I will just divide it on this side. It will be I naught by Is plus 1 is equivalent to exponential of VL by Vt 1 plus VL by Vt. Okay, now here this term, so we have to see here V naught, this expression, where is the expression? I have written it. Okay, here IL is equal to I naught minus Is exponential of VL by Vt minus 1. Okay, so this I naught here. Okay, here this expression. Can you see the notation A?
Yes, sir.
Okay,
Yes.
so see here. This is I naught by Is plus 1. Can you see I naught here? This is Is and this is your IL. So I can write it. Wait, just let me just write it again. So IL is equal to IS. IL is equal to I naught, sorry. IS exponential of VL by Vt minus 1. This will be I naught. Wait a second, this is IL. Okay, so this is Is exponential of VL by Vt minus 1 is equal to I naught minus I L K I L P E. Wait a second. Wait a second. Let me just check. Wait a second. Mm, Okay, so this is how it is. So this is your I naught, okay, and this is your diode, and there's a circuit here. This is your VL, right? So
Yes.
if your device is open, what does open mean? That means current IL is not IL. What is the current notified here? ID. Okay. If your device is open, your IL is not IL. I device is, looking at the current. Okay, yes. Sorry, sorry. This is I diode. This is IL. If the device is open, no current flows. Is it right? This becomes VL becomes VO. That is called as an open circuit voltage of photodiode. Okay, one second. When open circuit, there is no current flowing. That means my IL will be 0, and from this relation, it will be I naught minus IS exponential of VL. Now VL will be simply V open circuit. That is VO. That is VO by VT minus 1 equal to 0. That will give me I naught by Is is equivalent to exponential of V naught by Vt minus 1. Okay, minus 1. That will give me 1 plus I naught by Is is equivalent to exponential of V naught by Vt. So here you can see that this and this term are same. You have to replace it by exponential of V naught by Vt. Okay? You replace it by exponential of V naught by Vt, and on right hand side you have exponential of VL by Vt 1 plus VL by Vt. Now taking log on both sides, what you will get? Log of exponential, it's log to the base e. That means log to the base e. Usually log to the base e is represented as ln. Just don't get confused. So it will be V naught by Vt is equal, and log of a into b is log of a
Log
plus
A
log.
plus B.
Log A plus log B.
Okay, so it will be here, it will again be VL by Vt plus log of 1 plus VL by Vt.
VL by VT.
Okay, this was the term we discussed last time here. So you had to do this one step. Okay,
Thank you, sir.
Yes, sir.
okay. Look at this. You can stop this session now. If you have any doubts related to MOSFETs, any basics, you can ask in the next session. Okay.
Yeah, sure. Thank you
Oh,
very much.
and apart from that, if you are undergraduate students, you can speak to me freely about anything you want to know, what further you can do, and what else you have in the future. So maybe I am a little bit 3, 4 years senior than you guys. So you can freely ask me about anything if you want to know anything. So feel free, okay? Okay, so we can end the session now.
Yeah, thank you.
Okay,
Thank you,
thank you
sir.
guys.
Thank you
Thank
very
you guys
much.
for joining.
Thank you,
Bye.
sir.
Bye bye.